Consider the following examples. The first one, let's think of the velocity of a breeze at several points in space. For instance, a beach. Um, say the beach is in our XYZ space. All right. So if you're thinking of the velocity of the wind, maybe the wind is coming. At this point, the wind is blowing really forcefully, and then it's still forceful, and then it kind of reduces and it reduces and so forth, and then it get forceful again and so forth. You know. So I'm taking the length of the vector that I'm drawing to be how forceful the wind is. Maybe this here like that and so forth. All right, so this is velocity of wind or breeze. Okay, so this is my first example. And now let's talk about, how about a hurricane um, or tornado? Well, let's do a hurricane. What does it look like? I think I'm thinking tornado, but when I draw it, you see what I'm talking about. It's like it's tornado. All right. So think about a wind in circular motion that's just going in circular motion and so forth. Okay. It's not quite easy to see, but let me draw it again. So this wind, and it goes like this, and it comes like this, goes like that, it comes like that, comes like that, comes like this, and so forth. Okay. So this is like the wind pattern of a tornado. Let's give you another example. So think about the heat exchange or heat exchanger on your ceiling. So maybe this is the pipe on top of your ceiling, something like that. And then the heat flows at a high speed here, maybe at a higher speed there. Maybe when it comes here, the speed slows down and so forth. All right, and then it continues to be high here. And another example I want to give you is the magnetic field. So this is the magnet. I don't know much about magnetism, but I know that if this is the north and this is the south, the magnetic field can go around from the north to the south, and the strength differs. The strength can be small at certain instances. So maybe along here the strength is small, and when it gets closer to the poles, the strength gets larger. All right, these are all examples of vector fields. And this would allow us now to give a semi-formal definition of what a vector field is. If we let F and G be defined on the region D in R2, okay? A vector field A vector field in R2 is a function f, capital F, that assigns to each point in D a vector f of xy, g of xy, right? So it assigned to each point, and the point would be, so the point xy. So we write it this way. The notation would be f of xy maybe f of xy will now be fxy, gxy, or sometimes we write it like this: f of xy is xy I plus g xy j. All right, so we can, this vector field can also exist in R3. So in R3 we'll be having x, y, z, and then the vector field would be something like fx. The vectors or the functions, the continuous functions we're talking about would be the functions f, g, and h, and then our vector field would be f, x, y, z is equal to f, x, y, z, I plus g of x, y, z, j plus h of x, y, z, k. All right, so that's in R2 and this is in R3. In R3. In R3. Okay. So a few things to note. Let's talk about continuity. F, capital F, is continuous if F, G, and H are continuous. Same thing with the R2. If F and G are continuous, then F is continuous. And F is differentiable if F, G, and H are differentiable. All right, so let's talk about this. So if you have a function that is able to give you vectors depending on where you are, all right? So if for the wind velocity, so if your point is here, then it gives you this vector, a long vector. However, if it's here, the function gives you this a vector that goes downwards. Maybe if you're there, it gives you a short vector and so forth. All right. So let's do a few examples of this. So we want to sketch representative vectors of each vector field. All right, so the first one is f of xy is equal to 0x. So that is just xj. All right, xj. So what does this mean? I want you to pay attention. So this vector field is in R2. So we have our y-axis and our x-axis. Y-axis, x-axis. Okay. So if you have a vector, think about the vector, or let's pick a few points. Let's pick a few points. Pick the point 1, 0. Pick the point 2, 0. Let's pick another point, negative 1, 0. That. And then let's pick the point 1, 1 and 2, 1. And then let's pick 1, negative 1, 2, negative 1, maybe 1, negative 1, negative 1, negative 1, and negative 1, 1. Okay? Let's play with these points. Okay. So let's start with this. It says to us, if we are at this point, the vector we get is the vector 0, 1. Okay? So at the point, so what am I saying? At the point 1, 0, our f, the f we get is the vector 0, 1, 0x, because x coordinate is 1 here. So this is just 0, 1. So what vector is 0, 1? Right? It starts here, and then it goes up 1 unit. Along the x-axis, it goes, in the x direction is 0, in the y direction is 1. So we have that, something like that. Okay? At 2, 0, that means it's gonna go up 2 units, right? Okay. At 1, let's look at 0, 0 is just gonna be that. Then at negative 1, 0, it's gonna go down negative 1 unit. So it's gonna go down this way. However, at negative 1, 2, or negative 1, negative 2. So for instance, at negative 1, negative 2, f, it's still just gonna be 0, negative 1. So it doesn't matter. So it's gonna be 0, negative 1. So it's still going down just 1 along the y-axis and not moving at all along the x-axis. Okay, so how about at this point? At the point 1, 1, it's still going to be 0, 1, and so forth. Okay, so think about this. We're seeing a pattern here. If we're at 1, we have vectors that are just moving upwards 1 unit, right? If we're at 2, we have vectors that are just moving upward 2 units, no matter where you start, right? If we're at 3, for instance, we have vectors that are 3 units long, and so forth. All right, so that means if we're at 1/2, then we have vectors that are 1/2 units long, like that. All the vectors are going to be like that, right? Here, all these vectors are going to be like this. Okay, all right, so that's what we have. That's our vector field in this case. If you have any question, write it down and ask me in class. How about f of xy is equal to 2x and 2y, right? Which is the same thing as just 2xi plus 2yj. Again, we're in R2. Let's pick a few points and see how this goes. Okay, so when when x is 0, 0, when x is 0 and y is 0, then we just have 2 times 0, 2 times 0. Let's pick an interesting, let's observe this a little bit. Let's see what happens when we pick 1, 1. When we pick 1, 1, then we have a vector that's 2, 2, right? So at the point 1, 1, our vector f of xy, or f of 1, 1, becomes 2, 2. So we just have a vector that is moved, that's 2 units up there, all right? If we're at the point, how about at the point, let's do 1, 0. 1, 0, then the vector is moving along the x-axis 2 units. So if we're at 1, 0, then f now is going to be f of xy, or just f, however you want to do it, is going to be 2x, which is 2 times 1, and then 2y, which is 0. Okay, so along the x-axis we're moving 2 units, along the y-axis we're not moving at all. Okay, if you do this for a bunch of points, you will get something that looks like a star, like that, okay, that's what you get. Of course, if you pick shorter, if you pick points, let's say you pick points here, your vectors are going to be shorter. All right, and if you pick points over here, your vectors are going to be longer, and so forth. They're going to be long vectors. Okay, so that's our vector field. All right, let's try one in R3. One example in R3. So let's try the vector field x, y, z is equal to 0, 0, 1 minus x squared minus y squared. And then we're looking at for x squared plus y squared is less than or equal to 1. So already we're being given a restriction here. X squared plus y squared is less than or equal to 1 is the cylinder of radius 1 that is parallel to the z-axis. Cylinder of radius 1 parallel to the z-axis. So that is my cylinder. Go down. Go down like that. Okay, not quite. Let me make it more centered at the y-axis, at the z-axis. Okay. All right, so we have okay. Okay. So let's pick a few points. All right. There's infinitely many points to pick here, but we can be a little bit wiser when we're doing this. Let's look at this. Our vectors are going to have the form 0, 0, and then it's going to be it's going to have values, only z values. All right. So that means along the x-axis, our function, our vector is not moving at all. It's steady along the x-axis. Along the y-axis, it's steady. Along the z-axis, that's only the axis where it has values, all right? So for instance, if we pick the point, let's pick the point 0, 0, 1, okay? at 0, 0, 1, what do we get? Or let's do a 0, 0, 0. Why not 0, 0, 0? At 0, 0, 0, our f is the vector 0, 0, 1. Okay? 0, 0, 1. So you get a vector that along the y-axis, there is no movement. Along the x-axis, there's no movement. But along the z, it's moving. It's of length 1 along the z-axis, of length 1. Okay? Now, pick another point. Let's pick another point. Let's pick a point at, think about at 0, 0, or let's pick at 1, 1, 0, for instance. What do we get? 1, 1, 0. All right. Then we get f is equal to, so this is 1, 1, 0. So that's where we're going to begin. This is where 1, 1, 0 should be. That's where we're going to start to draw our vector. We know the first component of our vector is 0, second one is 0, and the third one is 1 minus 1 minus 1. So we get minus 1. Okay? So at 1, 1, 0, we have that. All right? So, but that's where it stops for this vector field, because we're restricted by x squared being 1 and x squared plus y squared being less than 1. Okay, let's do a few more examples. So we cannot have x squared and y squared. We cannot have 1, 1, 1, 0 actually, because it doesn't fit into the cylinder. So let's delete it from our vector field, but let's still leave it that way. Okay, let's pick another point. Let's pick, say we pick the point let's pick another point, which is a 0, 1, 0. Okay, so 0, 1, 0, if you do 0 squared plus 1 squared, that should be less than or equal to 1. So I'm just making sure it fits with that. So f is going to be 0, 0, and then 0. Okay, 0, 0, 1. So it's going to be 0, just a point, a vector that's there. All right, let's pick now. Let's pick, how about 0, or let's pick 1/2, 1/2, and then 1/2, 1/2, 0. So I'm still stuck on the xy plane to really understand what's going on. So if I do 1/2, 1/2, I end up getting 0, 0, actually 1/2. All right. So at 1/2, 1/2, which is around here, I know I said that was where 1 is before, but it's not. So we get that. So what I'm trying to show you is that the closer we get to the origin, the longer the vectors become, right? And the farther we are from the origin, the shorter the vectors become. So that's the main thing I wanted to show you. So we're going to get vectors that are all moving up along the z-axis, but the closer we are to the edge, the closer we add to the origin, the longer the vectors become. The farther we add, the shorter it becomes. So that's what we end up with. Okay, that was a long example. I expect you to have a lot of questions. You can either just ask me your question on the comment, or just if you're taking my class, you can ask me in class. These videos, I make them in mind thinking that we're going to meet in class, but you can also just ask me questions in the comment. All right, let's look at another definition. A vector field F is said to be a radial vector field if it can be expressed in the form f of x, y, maybe z, is equal to rho of x, y, z. Rho is just a function of x, y, z, x, z, where rho is a scalar function. Let me call it, it's a scalar function. Scalar valued function. Okay. So one thing I want to mention is that radial vector fields always point away from the origin or towards the origin. So an example would be the vector field we saw before. So example, first example, f of x, y. We saw this vector field 2x, 2y. And this is the same thing as 2 times xy. This 2 is your rho, all right? And you remember what it looks like, what we got. The vector field was like this, like that, something like that. So it's all pointing outside the origin, okay? And then we had another, oh, we didn't, but I can show you another example. This is in R3. X squared, xy, xz. So this is a vector field that allows us to factor out an x, and we're just left with x, y, z. So your rho in this case, this is your rho in this case, rho of x, y, z. So these two are radial vector fields. All right, let's look at another concept. If assume that we have a function z, and z is q, or let's call it phi of x and y, xy, you know, let this function be differentiable. It's differentiable function on regions in R2, maybe just one region. So the vector field f such that f is a gradient of phi is called a gradient field. So this should make sense. The definition should totally make sense, because you just have, you're taking the gradient, and we know how to take gradients. So let me make this more general. Let's say x, y, z. X, y, and make it for R2, but it can also apply for R3. This also applies to in R3. Okay. Okay, a few things. The function phi is called a potential function. A potential function um, for f, capital F. Okay, and the level curves, of phi are called.
Someone from IT is here? Did you call IT?
Yes, can you give me 5 minutes?
Yeah, sure,
All
you
right.
wait. You wanna wait here?
Okay. Are called equipotential curves. All right. The flow curves the flow curves of F are orthogonal to the level curves of phi. This is capital F. All right. So the question, let's look at some examples. Let's sketch and interpret. Oh, well, let's do this. Let's sketch and interpret the gradient field. The gradient field associated with the temperature function. Temperature function T 200 minus x squared minus y squared on the circular plate R is equal to xy such that x squared plus y squared is less than 25. Okay, so if you look at the plate, this is the plate. Is a circular plate of radius 5. Now, let's find a gradient field, which is F, is a gradient of T, which is negative 2x, negative 2y. All right, so I'm just taking the derivative with respect to x and the derivative with respect to y. So look at this. This is actually a radial field. So this is negative 2xy. Okay. Since it's a radial field and it's negative, everything is pointing inwards. So pointing, the vector field are going to be pointing inwards. Inward. Okay. So remember that the gradient vector tells us the direction of greatest ascent. As we can see, the vector field shows that the diffusion of heat is inward. So that's what this is telling us, okay? The diffusion of heat is inward, all right? So we have this function for the temperature, right? and we're looking at it in this region R. This is our region R, right? And then the gradient field is pointing inwards. So the interpretation is that the diffusion of heat is inwards. So I'm going to give you something to try. Then I have to run because somebody's waiting for me. That's so interesting. I didn't see that in my calendar. Sorry about that. X squared minus y squared over 2. All right. So I want us to find a gradient field. Find the gradient field of for phi. All right. So that's all. Try this yourself. This is very easy. All right, I'll see you in class on the next video.